Problem statement. A single pump operating at 3,850 RPM conveys water between two reservoirs through a pipeline with a diameter D of 150 millimeters, a length L of 420 meters, a Darcy friction factor F of 0.025, and a total minor loss coefficient of sum of K equal to 6.4. The elevation difference between the two reservoirs is 30 meters. Determine the actual flow rate and the corresponding pump head for the 3850 RPM pump. So we know the actual flow rate and the pump head um, comes from the intersection of the pump curve and the system curve. So here is the problem is telling us to use the 3850 RPM pump. So basically it's telling us to use this pump curve. So we have the pump curve. So what we are missing is the system curve. Okay, so the system curve, then we can uh, determine using the formula, which says HP is equal to theta 2 minus theta 1 plus FLD plus sum of K Q square 2 times gravity area square. So HP will be equal to theta 2 minus theta 1 is 30. F is equal to 0.025. The length is 420. The diameter is 0.15. Sum of K is 6.4 times Q squared divided by 2 times gravity area square. And area is equal to pi times 0.15 square divided by 4. And all of that to the square because it tells us area square. And this will give us an HP equal to 30 plus 12,489 Q square. Okay, and HP is in meters, and Q, of course, will be in cubic meters per second. So that is the system equation. So there are many ways where we can solve this problem. One of the ways is the graphical method, where I can plot the system curve on the pump curve. So I can plot this curve here on this curve. Example, when Q is equal to 0, the system curve will give me 30, right? So it will give me 30. And then I can continue that to plot that to find the intersection. Okay, let's do that. So I'm going to then plot the system curve. Okay, so let's make a table here. Okay. So first, I have on the pump curve the flow is in liters per second. So I'm going to put here flow in liters per second. In the system curve, the flow is in cubic meters per second. So I need to make the conversion to cubic meters per second. And then the HP in the pump curve is in meters, and in the system curve also in meters. So I need only one HP in meters. Okay. So example, when the flow is zero, the system curve, uh, sorry, when the flow is 0 cubic meters per second, 0 cubic meters per second, the flow in liters per second. So we know that 1 cubic meters is equal to 1,000 liters. That's the conversion. So when the flow is Q equal to 0, okay, Q is equal to 0 in cubic meters per second, also will be 0 in liters per second. And HP will be equal to simply 30. Okay, so let's try for some values. Let's try for some values here in the in the pump curve. For example, we can try 10, we can try 20, we can try 30. So if the flow would be 10 on the pump curve, um, that for the system curve will be 10 divided by 1000, because remember 1 cubic meter is 1000 liters. So that will be 10 divided by 1000 will become 0.01. Therefore, in the system curve, we plug the value 30 plus 12,489 times 0.01 squared. That will give me a value of 31.25. If we do that example for the flow 20 and 30, we can do the same thing, and then this will be 0.02, and this will be 0.03, and these values will be 35, and this value will be 41.24. So now we can plot these values on the pump curve. Example, when the flow is 10 liters per second, okay, the head is 31.25. Okay, so when the flow is 10, this will be about 31.25. So we have here the value of 30. This is 35. So 31.25 will be more or less around here. More or less will be there. When the flow is 20, so we can draw a line again there. When the flow is 20, when the flow is 20, that will be 35. 20, that will be 35. So it's going to be the intersection of these points. Okay. And then when the flow is 30 liters per second, which is here, this will be 41.24. So let's see, we can draw again a line here. Okay. So if the flow is 30, it will be 41.24. So this is 40, this is 45. 41.24 will be more or less here. So I can join those points. I can join those points. Here. And I can find the intersection. The intersection of the pump curve, which is this one, with this one will give me this point. Right? That is the intersection. And then I can read the flow discharge and the pump head from this curve. So we can say, okay, the flow discharge here, then it's going to be about this value. So it's not 25, it's a little more than 22.5. So it's more or less, we can say Q is going to be about 23.5 liters per second. And the pump head also can be obtained by drawing a line here. Let's see if we can find a horizontal line there. So that will be about, it's more or less 35, it's more or less in the middle. So HP will be about 37.5 meters. And that will be the answer to this problem.